This is John Black, Super Chemist. This is just me talking. There's no experiments during this video. Just a little bit of nomenclature about oxyacids. First, I want to go into about halogens. Halogens are your group 7, or I guess nowadays they call group 17. Either way, it's the group that has the valence electrons of 7, right? They're really electronegative because they only need one more valence electron to fill up their whole valence orbit there, and that would make them like royalty, or they'd be noble then, or noble electron configuration, and that's what they want. So, anyways, here's the list of that group, the halogens. It starts out with fluorine, chlorine, bromine, iodine or iodine, and whatever whatever that represents. It's probably radioactive. Fluorine and the AT chemistry, you really don't deal with it that much. It's mainly chlorine, bromine, and iodine. At the top of the list, it's more electronegative. Bottom of the list, they're bigger, they're larger. You know, fluorine is smaller than iodine. It's smaller than chlorine, chlorine smaller than bromine, etc. If you think about it, why is that? Because when it's small like this, those valence electrons, they're close to the nucleus. You know what I mean? And the nucleus is what's pulling them in, right? That's what's, you know, the positive, and the electrons are the negative. They are more electronegative because they don't want to give that away. It's like two magnets that are close together. Iodine is so big and so large, yes, it wants to fill up that octet. It wants an extra electron. But, okay, the electrons are, iodine's giant. The electrons are so far away that it almost, you know, it's like two magnets far away from each other. And then here you got two magnets close to each other. Which one's going to fill it more? The one that's close, obviously. That's why these are more electronegative. The larger it is, they're less electronegative. Now I want you to keep in mind, chlorine, bromine, all the halogens, they're diatomic. They don't just exist like helium would exist by itself. But chlorine, bromine, iodine, they all exist with themselves. You know, two chlorines, two bromines, two iodines. It's not a salt. It's not an ionic bond. Since both, you know, you got two of the same exact things here. Two same atoms. Chlorine, two same atoms. Bromine, two same atoms. Iodine. So they're not salts. They have the same exact, you know, want for that, the sharing of the electrons. That bond between these two chlorines, they're equal, you know what I mean? Because they're both as strong. Either one is, you know, it's not like hydrogen chloride where the chlorine is grabbing up the, you know, it's bigger and, you know, more electronegative. It's pulling. These are the same electronegativities. They're the same size. They're the same everything. And chlorine and chlorine's the same. So it's a covalent bond, not ionic. That's why they're soluble in nonpolar solvents. Because of that fact, because of these, it's not really ionic. You know what I mean? And that's why iodine is not that soluble in water, and so forth, because they're not, these aren't salts. Alright, now what is an oxyacid? An oxyacid is just an acid that has oxygen in it. That's it. Hydrochloric acid is a well-known acid, so let's start off with the halides, okay? Sure you know hydrochloric acid, hydroiodic acid is with the iodine. But I want you to look at these, how they go. The first one that has only one oxygen is hypochlorous. 2 oxygens, chlorous. 3, chloric. 4, perchloric. 5, or no, this is not an oxyacid. This is a hydroacid acid. has no oxygen, so it's not an oxyacid, but that's hydrochloric acid. I want you to notice how there's a pattern here, okay? Look at the next example, and also that all you have to do, if this is iodine or bromine instead of chlorine, you just take the CHLO out of there. See how, I mean a CHLOR. You take that out and you put BROM for bromine. If it's iodine, you put IOD for it. If it's sulfur, you put sulfur for it. It's that simple. Okay, and I want you to show you, and that's easy up here for these. I want to show you the sulfur one, okay? Look at sulfuric acid. Now, it can't have just one oxygen. It has to start out with two oxygens. Just, you know what I mean? So it takes that first form, hypo, OUS. Prefix hypo, suffix OUS. Now look what comes next. If you just change the CHLO into sulfur, look at this. Sulfurous. See? Chlorous. Sulfuric, chloric. Persulfuric, perchloric. And then the kind of gets off, you know, the H2S that doesn't have any oxygen is different. It's hydrogen sulfide. But you see how there's like a pattern going, right? Now the pattern isn't, you know, exact for every one. Here's some examples of the nitric acid. You got hyponitrous, you got nitrous, nitric, and peroxynitric. See how they put the oxy in? But it's still just per with nitric in it. You know what I mean? That's it. You replaced everything with NITR. Okay? Now keep in mind, the OS doesn't mean a certain amount of oxygens. As you can see here, it means one here, and here it means two, right? What it means is it's the least amount of oxygens that that oxyacid can have. And then you work your way up. You know what I'm saying? You know, if you know that the lowest one is 2, then it's hypo OUS. You know the next one after that is OUS. One after that is IC. One after that is per IC. You know what I mean? Or close to it. Alright? Same way with the phosphoric acid. You know, it kind of deviates too. But I want you to see that there is a somewhat of a pattern going on there. Okay? Now let's check this bottom of the page. Alright, so now, what happens when you put chlorine into water? You get an oxyacid, hypochlorous acid, and hydrochloric acid. Now if you want, you can put some UV light on that, and this will all decompose to HCl and O2. Oh, I have it down here. See, right here is the formula. And you could have all hydrochloric acid. Of course, you'd have to watch that the O2 doesn't build up and, you know, make any too much pressure. But my point is, we did that in a video already. We made hypochlorous acid, right? We bubbled CO2 through water. We also did this. It's the same exact thing, except we replaced the bromine and chlorine. Everything else is the same exact. You know, you just take the Cl and put a Br, right? So we made hydrobromous acid. We did that in the video. Now, iodine isn't that soluble in water. If you want to make HIO and HI, then you have to do it a different way. I think you put some kind of silver nitrate maybe in there, salt. You have to put some salt in there or something to maybe catalyze it. I can't remember. I'm not going to do that though. Let's go to the next page. Alright, so we saw you put chlorine into water, you get the hypochlorous acid and hydrochloric acid. Now how do you get the salt of that acid? Right? You just use sodium hydroxide instead of water. You don't even have to know the rest of this. You should just look at this and be like, what was replaced? This is water, but an H was replaced by Na. So that means you're going to have the same thing here, but an H is replaced by Na. You can have the same thing here, but H is replaced by Na, sodium chloride, and then you end up with water too, because everything's a little bit off. But you see how it's the same exact equation almost. The only difference is you're replacing H in the water by sodium, and that's it. And you got to do the equation a little bit different because it doesn't stoichiometrically work out perfect. You know what I mean? So you have to put 4 here and add 2 water, and these are 2s. But you see my point? It's the same exact formula, and this is the same for bromine. You can just take all the Cl's out and put Br in. You know what I mean? Another thing I wanted to bring up was something called disproportionation. Okay, disproportionation is when you take a molecule, you divide it into 2 sections. One of the sections is oxidized, and the other section is reduced. Okay, so one goes up in oxidation, one goes down, right? I want you to look at chlorine. How does this happen, right? How does it happen? H2O is right here. When you split up H2O, you got a positive proton and a negative OH, right? Here, if you split up the chlorines, they're equal. There is no positive and negative. It's a covalent bond, remember? So when you split the Cl's up, they're neutral. Cl, Cl. Now, if I give a proton to one of the Cl's, it went from neutral to positive. That means it went to having no money to having some money. So it got oxidized, right? Now the other chlorine, remember, it's neutral. There was covalent, so it's a neutral thing. Now it's getting a negative thing. It was neutral, it had no money, and now it got a bill. Someone took some money off of him. Someone gave him a bill. Now he's even below having. He's less than neutral. Okay, so he got reduced, right? And if you look up here, here's your Cl. You added the proton, and here's your OH. See, you got your Cl. You added the OH here. And this one you added the H. H2O. Now in the next video, I'm going to make some sodium hypoiodite, which would be basically bleach, but instead of using chlorine, we're using iodine, right? I'm going to do the same thing as this second reaction here. Iodine and chlorine, they're the same thing, right? They're both halogens having 7 electrons in their valence orbit. Then I'm going to add some sodium hydroxide. It's going to disproportionate this. One of them is going to get an O, what would be an OH, but we're using sodium. So one of them is going to get an ON, and one of them is going to get an N. Instead of H's, because you probably get H's. But anyways, now the whole reason I'm doing this reaction to make this is because there's a way to test for methyl ketones or secondary alcohols that can be oxidized to methyl ketones, and I'm going to do that test after I make this sodium hypoiodite. So anyways, this is a nice short easy video. I'm just going over some nomenclature, and you all have a great day, and always remember, science is great.